Hello, welcome to the ICAP tutorial. This is the first one. There will be a general introduction about ICAP. ICAP is one of key-size device characterization and modeling software. The full name of ICAP is Integrated Circuit Characterization and Analysis Program. It can be used for integrated circuits as well, but it's more common that it's used in the device level. Here, the device and main transistor level. ICAP is an open and flexible environment. It has wide choice of simulators. The internal simulator of ICAP is HPE SoftSim, which is the EDS core. You can also call external simulators like HSpice or Spectra to do the simulation. And it allows programming. There are two languages supported in ICAP, the PL and Python, and it has powerful optimization and advanced graphic capabilities. Besides the modeling, you can also do measurement using ICAP. It has extensive library of instrument drivers, and there is a built-in wafer pro with it. You can do automated measurements. And also it has efficient data flow and storage. Besides using the open platform to create your own models, there's also turnkey modeling solution supported in ICAP. There's RF extraction modules for HBT, FET, and HEMT. There's also CMOS modeling packages, and there's also GAN CMC examples. Besides the traditional measurement and modeling, there is also an AN toolkit. You can use the artificial network toolkit to generate a model based on measurement data. And at last, the model generator is a new tool to organize the extraction flow, and user can customize and develop their own auto extraction flows in the model generator, and it supports the recentering function. Overall, it's a very productive software, and you can do lots of customizations. With this one platform, you can do measurement modeling both for DC and RF, and you can also use the latest AN toolkit and the model generator. Now let's take a look at how the software looks like. Let's open ICAP. It pops up two windows. One is the main window and one status window. The main window allows users to open multiple modeling projects here. For the status window, we can see there's ICAP output and ICAP warning and errors. The output from the code will be showing the ICAP output part, and the warning errors will be showing this part. Let's get familiar with the buttons in the main window first. Create a model, open existing model, and open an example in the ICAP default folder, and save the model. Go back to the next step. Cut, copy, paste. Start wafer pro is for automatic on-wafer measurement, and the PMG is for power electronics model generator. And start model generator. Start data viewer. Open the hardware setup. Open the simulation debugger. There are many examples in the ICAP example folder. You can open it from the examples. We'll use a very simple diode model as an example. So let's open the model files, diode. Let's open the diode model appears on this main window. We can double click on the diode to pop up a new window. This is another important window for ICAP, the model window. The ICAP model file contains different hierarchies. First, let's take a look at the model level. It contains all the duties and setups, and then the circuit. The circuit part allows users to put a list of the model here, or user can call model from an included model library. But all the parameters in the circuit part will keep to the original value, you put it here. It doesn't change. And then comes to the model parameter part. It lists all the parameters for the model you put in the circuit part. The values in this table will keep changing when you tune or optimize the parameters. And in the model variable part, the variables here will be used in the model level. The common one we can see is the simulator. You can put different simulators like ADS, HSPICE, Spectra here. And then comes to the macro part. The macro part is a place allow users to do some programming work. You can use PL or Python. Usually you can put some README files here, and also you can develop some code here to manipulate all the duties and setups from a higher level. Then the duty level. In this diode model, the DC and CV, these are two duties. Let's take a look at what's in the duty level. When you click on one of the duty, there's new tabs you can see here. First one is the test circuit. The test circuit you put here will be only applied to this DC duty. It doesn't work for the other duties like CV. The duty parameter contains the parameters for this, and then the duty variable. The value of the variables put here will be only applied to this single duty. It doesn't work for the other duties. A common way to use the duty variable is that suppose you have a device with different geometries, and each geometry is a duty. The width, length, those instances will be different for each duty. You can put that variables here. Then we can go to the setup level. In this diode model, the IDVD and CGD here are two setups. There might be several setups below one duty. Let's take a look what's in the setup level. First is the measurement and simulation. User can define the input, output here to measure the device, or import the measurement data here and then do the simulation. We can see for the output part, there's a type. You can use M for measurement and S for simulation and B for both measurement and simulation. And for the input part, you can define the mode, the node. The unit is for the measurement. It corresponds to the SMU you use for the measurement. And also you can set compliance and sweep type and order the points. Then the instrument options. If you use this setup for measurement, when connected to the instruments, you can see instrument option here. And then the setup variable. These variables defined here can only be used for this single setup. And then the plots part. You can define plots here to visualize the curves you measured and simulate. For example, this is the IV curve of the diode by display. You can see both the measurement and the simulation values. And the plot is very easy to define. Just add a new plot and give it the correspond X, XY data and the plot type. If you want to modify the plot, you can double click on it to pop up a new window. The report type you can choose as Y graph, a Smith chart, histogram, etc. And the x-axis is for log, linear, and dB, and also for the y-axis. And then the extract and the optimize part. This is another place allow user to do programming work in addition to the macros. User can create different transform here for extract, for pure coding. It also allows user to create an optimized task. You can choose the target and the corresponding parameters to create an optimization task. And the options allows to upper bound, lower bound, those things. Another common used transform type is for data processing. For example, you have some measured S parameter data. You want to do the embedding work. And also you need to transform the S parameter data to Y parameter data or Z parameter data. You can do that work here. Now let's take a look at how to do simulation. We have the input VA and that's the first order sweep, and VC as a second order, and IE as output. To do the simulation, you can simply click this simulate button. It will simulate this setup. And we can open the plots here. This is the metadata and the curve we can see. And go back here. If we need to see the measured and simulated data value, we can open it from here. Select the output and view data. You can see all the data values. And also for the input part works the same way. Another way to view the data value, you can check it directly on this curve by right-click and view data. So you will be able to see the VAIA, the output and the input measurements and input simulation value. Okay, the next step, how to tune the parameters and how to do the optimization. Let's go to the extract and optimize part. We have some optimization steps available here. We can use it directly by select the optimization step here and then select the tuner. And then you can use your mouse to tune these values manually. This is how it works. We can, when we tune the parameters, the simulation curve change at the same time. And after you finish, just click OK. This is for manual tuning. And then how to do the optimization. This is already an optimization step. We can just run it automatically by click the FX. So it's getting close and run it again. It's getting closer. And then run it several times. You can see the simulation value almost back to the original one. Another way to do the optimization is using the plot optimizer. On the open plot, you can open optimizer and then select the parameters you want to tune for this curve. You can also do manual tune here. First of all, we need to enable the plot first by click the P.O. button and then open the plot optimizer, and then you can tune the parameters from here. After finished, click OK. And you can also do an optimization by using the Run Optimization button. We can see we get a good fitting through this optimization.